My name is Sean Lurch, and today I'm going to talk to you about my honors research at Princeton Plasma Physics Laboratory. And the project I ended on was the effects of audio modulation on the corona of a Tesla coil. I worked on a couple of projects while there, but first I'm going to give you just a little bit of background about Princeton Plasma. It is run by Princeton University, but it is funded by the Department of Energy. The primary focus is on fusion energy and plasma physics. And here's a picture of the laboratory. So I interned in the science education department, and the reason I am there is because of the community college initiative. And over the summer I'm actually going to continue my internship as a full-time intern, and I will actually receive a small stipend during this process. So the science education department focuses on a few things. They have student programs, which is like what I'm doing, plus a K through 12 component. There's educator programs for teachers and perhaps professors. One of the things they get to do is actually go down to Texas and fly in an airplane in microgravity. So they experience about 30 seconds of weightlessness, and during that time they get to actually perform experiments. There's also a public outreach component, and that includes the Science on Saturdays, which is a public lecture that everyone can come to. I think it's run in the spring. So we started with the plasma processing unit. And I'm not going to talk a whole lot about it, but essentially the long term is plasma processing via electron cyclotron resonance. And what this is a machine that ignites argon plasma using a microwave source, and it's under vacuum. And what happens is ions are created, and they are bombarded against basically a source of graphite, which sputters atoms onto a silicon wafer. And the product of this is thin films of carbon, which Andrew was working on, and he was trying to make some diamonds, I imagine. The original purpose of the machine was actually to use copper and to make thin films of copper. So this would be useful in things as perhaps making mirrors, perhaps for electronics, and diamonds, if Andrew ever got it to work. So this is a picture of the machine that was in the science education lab. And you can see here is a large magnet to hold the plasma gas. There's a robotic arm and some actuators that were used to move the silicon wafers into the machine. Up on the top there is the microwave radiation source, which is directed into the plasma. And you can see various pneumatics and cooling systems and exhaust systems. So before Christmas I was told this was going to be the experiment that we were going to get up and running again. And actually over Christmas Andrew decided to try to get it running himself. And I found out when I came back that we were going to be taking it down. And he had some problems with O-rings, and there was some leakage of radiation from the magnet, or from the microwave source. So when I got back, started to organize the manuals, I started disassembling the vacuum system, with Andrew's help of course. There's disassembled the pneumatic system, the exhaust system, the cooling system, and we wrapped everything in tin foil and put it on a shelf to be stored, till it'll be used again. So a little more interesting to me, because I'm an electronics engineering major, was the power system. And so I got to disassemble the high power system, probably some of the biggest power sources I've ever seen. There was a computerized control system, which literally had thousands of wires that we disassembled. And there was also some sensitive sensors that we wrapped in tin foil and put on a shelf. So after that, we started to transition, we completely broke it down, and this is actually the components of it, and we ended up wheeling it out of the room and into a neighboring part of the facility, and they're going to continue to break it down and recycle the parts for various other experiments. So during this process, we began the transition to the project I'm working on now, and Andrew brought with us today, he gave me a demonstration of this little plasma speaker that we have, and then he also showed me a Tesla coil that was laying on the ground from the Liberty Science Center. And he told me that we are going to be making a big plasma speaker if we can do it. So essentially, we started with this Tesla coil from Liberty Science, and you can see it's about 6 feet tall. And what a Tesla coil does is it produces an electrical discharge similar to lightning. And we are going to turn this into a plasma speaker. So you can see the control box there. This runs on a 220 amp line or 220 volt line. And it's a pretty big Tesla coil. So some basics about a Tesla coil. Essentially what you have is a resonant transformer, and that is two loosely coupled inductors, L1 and L2, and you can see those on the previous page. L1 would be here, L2 would be this tall portion, and those are both coils. And what happens is, well, I'll actually tell you that in the next slide, but there's also a high voltage power source, DC. There's L2 and C2 form a resonating circuit, along with L1 and C1 are a resonating tank circuit. And what happens is these will be coupled together to transfer power from the primary to the secondary. Now the tank circuit oscillates through the use of a spark gap. And the next animation will show you actually how this works. Is that working? Good. So this is not my animation, but it's definitely a great description of how a Tesla coil works. In fact, it's pretty simple. There's not a whole lot to it, but we're going to make it a lot more complicated when we try to modulate this and play music through it. So hopefully it'll finish, and I'll start from the beginning. So C1 charges, and what happens is that becomes a DC open once it's fully charged. That forces current through L1, and then it bridges a spark gap. When the C1 is fully discharged, basically the circuit starts to oscillate. Now what happens here is power is transferred from L1 into L2, and the voltage is stepped up tremendously. And through many cycles, essentially the charge is transferred to the top C2 toroid, which acts like a capacitor. And when the charge becomes great enough, it will discharge through the air to a grounding point. So this is definitely a good animation of how a Tesla coil works. So back to our M100, I contacted the manufacturer, and he told us that this was a 750,000 volt resonant transformer. It operated at about 300 to 350 kilohertz, and it would produce about a 5-foot discharge. So I also had the opportunity to read a long, lengthy textbook, not all of it, about the physics of a Tesla coil. And a lot of it was actually above me, but I did get a lot of knowledge on the operation and the physics behind how a Tesla coil works. And here you can see someone running a Tesla coil in their kitchen, and I believe it's discharging into everything in his kitchen, which is not really recommended. So the transformer, the DC transformer that powers this Tesla coil is very large. It's 15,000 kilovolts, 15,000 kV, 15 kV, excuse me, 15,000 volts. It runs at 800 milliamps, and that's about 12,000 watts. And for some reference, that's 10 times more powerful than an electric chair, and that will definitely power a small radio station. So while I was on the phone with the guy who made the coil, he said that this is deadly, very deadly. Any mistake, you're going to have serious consequences. So you need to be extremely cautious when you're working with this. So to confirm the manufacturer's specifications, we did some testing using meters and test equipment. And the reason we were going to do this is because we're going to build a Faraday cage around this Tesla coil so we don't discharge it into everything in the room like the guy in the previous picture did. So to do that, we had to determine the capacitance and inductance of the components that we had, and then we would calculate the resonant frequency. So I'm not going to get into many of the very technical details in the physics because I want to give a general overview, but that is the resonance frequency formula. So I used a device called a bridge, and basically an impedance bridge allows us to measure the inductance of the coil. And it operates basically by comparing the inductance to a calibrated capacitance and resistance. And you could sweep through basically different levels, and it will actually move that meter, and when it comes back to null, you have centered on the inductance of the coil. This machine is probably 20 years older than me, as some of the other machines are at the lab, which is kind of interesting. And this machine can also be used to calibrate, or excuse me, to measure capacitance. So we measured the inductance at several tap points, and the reason the tap points are available is to actually adjust the resonant frequency. I didn't show you the small toroid, but that top dome can be changed. There's 2 different domes that can be used. And what happens is you adjust the resonant frequency when you change those domes. So you also would like to be able to change the primary side of that circuit and match the frequency so you can transfer efficient power. So we have, at the ring 4 was 21 microhenries, and at ring 2 was 5.4 microhenries. To do the capacitance, it was much more easy, it was much easier for me. I used my standard digital multimeter and actually just found the capacitance using my meter. That is not accurate. It was actually 50 nanofarads. The meter just wasn't hooked up during that. So based on these calculations or these readings, we were able to calculate what the resonant frequency was, and it turned out to be 306 1,000 hertz. And that was right within the range of what the manufacturer had actually said it would be. So I also found there's a much easier way to do this to find the resonant frequency. There's another very old device called a grid dip meter. And essentially you take this meter and place it near the coil and you sweep through frequencies. And what happens is when you actually come upon the resonant frequency, you'll see a dip in the reading of the meter and you'll know that you have found the resonant frequency. So using the grid dip meter, we were actually able to determine that it was about 300 kilohertz. So our calculations were confirmed, 3 different ways. So after doing all this research and analysis, I actually got to write a small technical document, which I gave over to Andrew, which he then told me I needed to correct a little bit. And so now I have at least one technical document that I've written, and I'll be able to use that in the future. If anyone would like to read it, I can give you the link to that. So back to the Faraday cage, which I talked about a little bit, because we're going to build a Faraday cage for our Tesla coil. And instead of being on the outside, we're going to put our Faraday cage on the inside, because we don't want the room to be struck with discharge. But essentially a Faraday cage is a metal shield or box that is directing current to ground, or at least around the items that are inside the box. And we're doing this to protect humans and also equipment from electrical discharge. And we were hoping to minimize any RF radiation that would leak out from this device because there was harmonics involved. If we were running it with a spark gap, it would actually be very broadband spectrum interference. But I'll tell you a little bit more what we're going to do. We're not going to be running with a spark gap. We're going to build a solid state Tesla coil. So this is not my picture, but I essentially did exactly what's going on here. And I took a large piece of copper mesh, and we used a grid dip meter, and we wrapped it around the Tesla coil, and we used the meter again to find out what the resonant frequency change was. And found out it was actually not that substantial. I think we'll find out for sure when we actually build the cage and try to run it. But it appears that having a wire mesh did not induce too much extra capacitance on the circuit, and hopefully it's within range of the taps that we have, so we can adjust the resonant frequency if we need to efficiently couple this coil so we can produce a discharge. So I set about to design a Faraday cage once we had figured this out. And I used Google SketchUp, which is a free software I had a little bit of experience with. And it's 3D modeling CAD software that I've used to design a cage, essentially. I built in several layers so I could remove items, so I could add items, so we could actually see all the components individually, so we knew exactly what we were going to build. And here's a picture of my Google SketchUp, and you can see it's going to be pretty big. That person might not be to scale because I think I actually deleted her and added her back in. So I'm not sure exactly how tall she is, but it's going to be about 8.5 feet tall and about 8 feet wide. So the cage design did take several weeks. I only interned for about 10 hours a week, and so I had limited opportunity, but I was also working on stuff when I was not at the lab. But we took into consideration the RF discharge, the room dimensions. We're putting this into our lab, and we had to kind of work around the items that we have in the lab. Visibility was an issue. How thick should we make the mesh? Is that going to affect both seeing it and also audio? And of course safety is a big issue at Princeton Plasma. While I was there, they came through and did a wonderful safety inspection, and so I got to see this, like 15 people just like scouring around our lab, making sure everything was in proper order. So safety was definitely an issue. And in this picture, we actually just started receiving some of the pieces of the Faraday cage, and I quickly put a few things together just to make sure it actually fit, because I went through this whole ordering process and kind of never done that, so it fits, which is good. A little bit more about the cage construction. It's going to be built from Unistrut and Versabar, which is a slotted channel, which you can add supports to through bolts. And based on the Google SketchUp dimensions, I was able to calculate all the lengths we need, how much we're going to need, the exact parameters involved, and also how many connecting pieces we were going to need. And I built that into the layers so I could see everything individually and confirm that everything would work. So back to the plasma speaker, back to where this is all leading up to. Just a little bit about plasma speakers. Essentially, they're loudspeakers that use ionized gas, which is a plasma, as the diaphragm, as opposed to like a woofer or a solid diaphragm. And when you modulate that, you will have a similar effect to a speaker. The methods of production include a plasma arc and corona discharge. There's one other. This is a plasma arc here, and that is a corona discharge. We are likely going to be building a corona discharge type of plasma speaker. I'm not exactly sure of the plasma arc circuit construction, but that might also be something that we look into. There is a way to build a bipolar Tesla coil in which both ends of the transformer connect to each other, and it's tapped at the center through a center tap. And I've seen both ways actually produce, quite large arcs. So the physics are similar to thunder. So when you hear thunder, that is essentially what we're going to be trying to do in the lab. So this is a schematic of a vacuum tube, essentially primary side and secondary of a Tesla coil. And so we're going to remove the guts from, or at least we're going to leave them in place, but we're not going to use them. We're going to build a solid state primary to run this Tesla coil. And then we're going to feed in audio and modulate it through the vacuum tube and hopefully transfer that into the Tesla coil, and then the spark itself will be playing music. So some basics about amplitude modulation. So you have a carrier frequency, which we're going to oscillate at 300 kilohertz, and that will couple with the secondary of our Tesla coil. And we'll modulate audio onto that, and we'll be able to transfer both the 300 kilohertz plus the audio to the secondary, and what you will get is music coming out of the plasma arc. So here's just a little animation of how amplitude modulation works. So this is going to continue through the summer. Like I said, I'm going to be there in a full-time job, which is really wonderful. I've been working with engineers and technicians. It's been pretty marvelous to kind of get an idea of all the layers in research, from the engineers to the guys who are building this thing to me who is helping this whole process. And hopefully we're going to see what the effects of audio modulation are on a corona of a Tesla coil. And it might look like the one on the left, or it might look like the one on the right. We're not quite sure yet. But it should be very interesting, and we'll see what happens. So a few other things while at Princeton Plasma, just to kind of finish up here. The Lieutenant Governor stopped by, and we showed her our plasma speaker. So got to meet the Lieutenant Governor, got to go down some pretty interesting hallways leading to the fusion reactor. This is actually underground and almost, a couple hundred yards long, and it's bent to prevent radiation from coming back to the control room. This is an unbuilt fusion reactor that's kind of sitting in pieces next to our lab, and occasionally they open up the door and let us see it. And I also got to see some amazing machinery. This is a gigantic lathe. You could probably build spaceship components on that if you wanted to. There's some ion sources, and I also got some hands-on with the technician I work with in using a lathe and some other devices and building some of the components that we're going to use. So I'd like to acknowledge the people that have been with me throughout this process, including Andrew Zwicker. He is the head of the Science Education Department. Larry is the technician that I work with on a regular basis. Aaliyah Morali is the person who introduced me to Princeton Plasma, showed me around, got me set up. Everyone at the Princeton Plasma Education Department, there's a few other people there, including Dee Dee and Steph. Of course, Professor Jin Rong. And it's kind of interesting how this all came about. I was sitting outside in the hallway and just happened to run into you, and you're like, well, why don't you go to Princeton Plasma? It might be great. So it was very, happenstance how it all came together, but here I am. And of course, Mercer County Community College and the Honors Research Program. So with that, we brought the little plasma speaker, and I think we're going to turn it on and let everybody see it. But if there's any questions beforehand, I'm more than willing to take them.
Sean, what's the advantage of a plasma speaker versus a traditional type of speaker?
Well, there's a couple of advantages. Essentially, the fidelity is a little bit crisper because plasma allows you to very precisely replicate music. I've read some things about how there would not be degradation of the diaphragm itself over a given time. There's actually some disadvantages to it, it replicates higher frequencies a lot better. If you think about low frequencies, you need like a subwoofer, which is a much bigger diaphragm. So that is actually why we're going to build the biggest possible plasma speaker, to hopefully move a lot more air and be able to create some of the lower frequencies.
Thank you.
So you modulate the discharge current,
Yes.
right? With the AM modulation.
Yes.
And how much power do you expect to be in the discharge in the first place?
We are going to build it about 2,000 watts.
That's very loud.
Yeah, so we're going to build a solid state primary about 2,000 watts. But there's going to be power loss through the coupling to the secondary. And that's why we're using vacuum tubes as opposed to integrated circuits, because the the transistors tend to burn out, we found out. So we're going to use a vacuum tube, and I've seen some of the ones up there that are very large. So it could be very interesting. But yeah, about 2,000 watts is what we're planning right now.
Right, and a fraction of the power is going to be coupled into center.
We estimate that our coil is about 60% efficient. It has to actually be loosely coupled to facilitate the ring up, because if it was very tightly coupled, the ring up would not be as substantial, and then you would not get such a large discharge. So the loosely coupled part is actually built into the circuit, which allows for the discharge to occur. But we're estimating 50 to 60% of that power will actually make it through. Yeah. You guys get it? Right on. So let's play some plasma speaker music. If you guys are interested.
Should we turn off the lights?
Yeah, I guess so. I've actually never given a demonstration. No, I think I can get it on and stuff, but if it catches on fire. I took 20 minutes, didn't I? Is it on? I picked Modest Mouse. You can play anything if you guys want. But this is essentially what we're planning on building on a very large scale. You good?
What if you think it was dedicated to that?
I actually can't hear you. Oh yeah. Well, you could see induced capacitance of a human. When you actually come near it, I happen to be very capacitive, and so is Andrew. You can actually change the resonant frequency of the coil and actually stop the music from playing because we're limiting power transfer. And Andrew told me to show you guys. Aha! So you can see that power is actually being dissipated way beyond the corona discharge. In fact, it's quite a bit of distance. Have you ever been to a science museum? You can see this in action. They have to have people holding, fluorescent light bulbs and walking around their very large coils. And Tesla had some ideas about wireless power transfer to be used commercially. And one of the funny things I learned was that the reason it was never going to work is because there's no way to meter it. So they never knew actually who was using what power. It was very hard to determine that. But you can essentially transfer power wirelessly in this fashion. What do you guys think? All right. Thank you, guys. I appreciate it.